Give you another minute or two.
All right, I'm ready.
What's the technique for the first one? Use up. What's U?
2x minus 2.
What's DU?
2. 2.
Dx, which means that dx is du over 2. So did you get something like 1/2 cosine of u du?
I did get that. Yep.
1/2 sine of u plus c, or is it negative 1/2? Positive 1/2. 1/2 sine of 2x minus pi over 2 plus c, senor. Are you with me? Okay. Area enclosed by. There's your downward opening parabola and your line with a negative slope. I understand the region. I see it's exactly one region, not two. And what do I do next?
Where they intersect.
The intersection points. 2 minus x squared equals negative x at 2 and negative 1. Yes? 2 and negative 1. My integral then goes from negative 1 to 2. What's the integrand?
Parabola on top.
Parabola on top. Upper minus lower. And so if you integrate that and evaluate, what's your answer? 9/2, or 4.5 is correct. You don't have 4.5, go back and figure out where you went wrong. All right, moving on to today's lesson. This is a good one. This goes to understanding calculus down, now getting the idea of how calculus can be used in a lot of different applications that you might not have even thought of. So, some of these are physics, some of these are more like civil engineering, I guess you'd call it, but we'll talk about that. In my math classes before this class, or in non-AP based, non-calc based physics, you did rate times time, yeah? You had to do this algebraically. For example, if Joe does one problem every 3 minutes, how many problems completed in 30 minutes? 10 problems. Now that's going with the assumption that, what?
He doesn't slow down.
The rate is constant. Yeah, you can only do constant rate problems before calculus. But with calculus, you could do varying rate problems because you start to understand that it doesn't matter if the rate varies. I can still take many little rate times time calculations, in fact, infinitely many rate times time calculations, and the integral adds all those rate times time calculations and gets a total amount of work done. All right? So the integral, or integral calculus, accumulates change. Moving on then, say, actually, let's continue in algebra base. Darn it, I was ready to get to calculus. Joe pushes a rock with a force of 5 newtons, a distance of 3 meters. How much work does he do? How do you find work? How do you find work? Force times displacement, yeah?
Yep.
In this case, what's the constant force you're applying?
5 newtons.
5 newtons. And what's the distance or the displacement we are traveling?
3 meters.
3 meters. What is a newton meter? Joule. 15 joules. Work is joules. All right. Now, if, however, instead of the rock being pushed over an even surface that was exactly the same, maybe I pushed the rock over a little hill and then through a puddle and then through mud, would the amount of force required be different? Yes, it would. Okay? That then would require calculus. So let's go with this. I was going to dump it, but let's keep it, okay? So, in calculus, you deal with more complicated problems like what if the rate varies? Say Joe starts at one problem every 3 minutes. But with every passing moment, he gets more and more tired, and his rate is half as fast every minute. Would you give me an equation for his rate as a function of how many minutes have passed? Go. His rate is a function of minutes. some people can just see the equation in their magical little minds, but some might start with the table, say, oh, let me do a few numbers to get a feel for what's going on. ¿Listos? Sí, okay. So, what is your function? Rate is? You said C, you're not ready at all.
I never said I was. Come on, Bailey. Gosh. Oh,
The rate at time 0 is a third, yes? What's the rate at time 1?
1/6.
1/6. Don't calculate, instead show where it comes from. What's the rate at time 2?
12.
A 12th, which is a third times a half, or a third times a half squared. What's the time of rate, or time? What's the rate at time 3? 1/3 times a half. How many times? 3. So at time t, it's 1/3 times 1/2 to the t. What are the units on that? Problems per minute. Algebraically, is that the same as 1/6 to the t?
No.
No, that's ridiculous. Is that the same as this?
Oh, gosh, no.
Yeah.
Why not?
Yes.
Yeah, that t applies to the 1, not the 2. That is nonsense. It must be a parentheses. Okay, it's got to be a parentheses. Okay, now that said, that's good stuff. How long would it take him to do 25 problems? Try it in your calculator if you want. You may use your calculator.
As I said in my calculator, I don't think it's
That's a small. Like insane. I did this wrong on the test. I don't know.
Okay, so what do you reckon? Let's talk about it together. Let's get started. What's something I can try? Graphing it. Okay, so that's what R looks like. Cool, now what? The integral from 0 to x of
RT.
where x represents how long it's going to take. Okay, to then what? Equals 25. Good stuff. Now, if you try that, your calculator can do an integral defined function. If you do something like that, you probably should have a dummy variable there.
Probably did this last period.
Okay, it did. I did. Yes.
So
Yep. Okay, so I'm saying how many little rate times time calculations of problems per minute times minutes would it take to finally get 25 problems? Yeah? Okay. Now, you will find that if I need to know when this equals 25, what should I do next? I guess I could trace along until I see a y of 25. That's kind of the amateur hour way to do it. What's another way? You could remember how to see when a function reaches some point, you then graph the point. So for example, you could, then use the intersection. So if you hit, what the heck? If you then graph 25, now
did you graph the integral?
I graphed the integral, yes. Okay, now if you try that and look for the intersection points. Feel free to change your window to 1 times 10 to the trillion.
Wait, so what?
Okay? So here's the problem, okay? The rate is getting too small pretty fast. So last class we said, well, what if it was just getting 5 problems done? So change it to 5 instead of 25. Does he get, how long does it take him to get 5 problems done? Now, the blue is the integral defined function. How much problems he's done at a point in time. And there's 5, yeah? Now I tried 1,000 for my window, 1,000 minutes to get 5 problems done. Still not yet, okay? I changed it to, then students ignored me and the whole rest of the period they're changing, I'll try 1,000,000, I'll try 1,000,000,000, and they didn't even listen to the whole rest of the lesson. Well, I can tell you, it ain't never gonna happen. He cannot get 5 problems done. He cannot. If he worked to the end of time, he would never get 5 problems done. Ever. Now, here's why. Consider this, okay? Let's look at this with rectangles here. On this first second, would you agree his rate at time 1 is greater than his rate at time, his rate at time 0 is greater than the rate at time 1. So even if I used left rectangles, and I said, in that 1 minute, how many problems does he get done? How many problems does he get done in the first minute? A third of a problem. It takes him 1 minute for every 3 problems, so in 1 minute, he only gets done a third of a problem. You with me? In the next minute, what's the greatest possible rate but 1/6? So from time 1 to time 2, how many problems does he get done? 1/6. Now 2 minutes have passed, and he still hasn't completed a problem. And at time, from time 2 to time 3, how many problems will he get done? A 12th. And then from time 3 to time 4, at most, he could get problems done 1/24. So the problems done is 1/3 plus 1/6 plus 1/12 plus 1/24. Let's see how good you are with pre-calculus. What kind of series is that?
Geometric.
Geometric. Do you remember the formula for infinite geometric?
Oh wait, it's A1 over 1 minus A1.
What is A1?
That's right. 1/3.
And what's the common ratio?
1/2.
This, he approaches getting, as time goes forever, he works forever, he will approach 2/3 of 1 problem done. And that is all. He'll never get it. Okay? Yeah. So you should just quit, am I right? All right. That actually was not my intention, but I kind of like how it turned out, so whatever. All right. Would you go back to, go to this question. These are more doable now. That was just a side note. That was kind of fun. What pushes a snowball? Now, because it's a snowball, the amount of force required is going to change. Okay? Okay? The force required varies with distance from the starting point. If the force is 2x newtons, find the amount of work required to move the snowball 7 meters from the starting point. So, big idea of both physics and calculus is work is the accumulation of many force. Actually, let's say many force over displacement problems. And because the force is changing just in 1 tiny centimeter, you have to make lots and lots of calculations, and therefore this is calculus. And that force, instead of a true delta x, is more of a theoretical microscopic change in x, which is dx. And that is from where to where? 0 to 7. Now, that's the hard part. The calculus is as easy as it gets. We're integrating 2x. If you can't integrate that, get out. What is the antiderivative of 2x?
X squared.
X squared. You're going to have to get out. So what is the work? 49 units? Joules. 49 joules. Okay? Easy enough. Let's try another work problem. Spring stretching. All right? think you'll also agree that stretching a spring gets harder as you get further and further from its resting point, okay? And so because of that, it's a natural calculus problem. I don't know how you did this in algebra-based physics, but in calculus, it's a walk in the park. Okay? Force for spring problems is dependent on two things. The spring constant that relates to the kind of spring it is and how kind the spring is, and then how far you're stretching it, that's x, yeah?
Yep.
Now, if I want to then figure out how much work is required to stretch it over a certain period of time, again, I'm going to have to use calculus because every time you move it, it's a totally different amount of force. So I'm going to have to accumulate the sum of many force over small changes in position or displacement kind of calculations. The force, in this case, is governed by the spring constant formula kx, where in this case k is 7. And where are we moving from and to?
From 0 to, or wait, no.
From at rest, which is 0 to
1.
1. We're stretching at 1 meter. That's a garage door spring. I don't know if any of you put on a garage door spring, but they're really heavy duty. It is 7x squared over 2 from 0 to 1. And therefore,
7 halves.
7 halves.
Kilograms per 2 kilograms.
Oh, sorry, I didn't. So it's the constant was kilograms per second squared. The x is in meters. What is kilograms per second squared times meters? That's newtons, and then times the dx, which is also meters. Newton meters is joules. Okay. All right. This one is more fun. I could get books. We could do applications of calculus problems of little rate times time problems all day, and there are that many applications. These are just a small subset. This is one that interests me. For civil planning / engineers / politicians trying to figure out how to plan your city, there is this idea called population density. The big idea generally is that there are certain places where people want to live by, whether it be downtown or the beach or the mountains. And right close to those, the ocean, you have high demand, maybe not high density anymore because rich people buy it all the land. But in terms of, generally speaking, the density is greater around that place everybody wants to live, and as you get further and further out from that place everybody wants to live, the density gets less and less, yeah? Now, that then makes things a little complicated in terms of trying to figure out how many people are in this area, because different areas have different densities. In this case, trying to make it a pretty straightforward case, you have a beach.
Oh. That's embarrassing. That's embarrassing. Oh my
Sorry.
gosh.
It's weird.
Hey, Jerry,
Okay.
say it. I thought you said, hey Siri, bro.
Yeah, this happens. Series is a big part of Calc 2, and all second semester always staying good. So here is the beach, or here's the water actually. The beach is over there. My bad. Okay, so if we draw a little shark or a little swimmer.
I'm gonna draw a shark. I'm gonna draw you.
Okay, a shark eating the swimmer, whatever you want. Okay,
It's like a shark.
but I digress. So everybody wants to live by the beach, and so in this case, the density by the beach is very thick. A lot of people want to live by the beach, so there's a lot of people per square mile there. As you get further from the beach, the density gets less and less and less. And less. So the density varies as you get further from the beach. Now the question is, given you have a density function that tells you how many people per square mile, when you tell it how many meters or miles from the beach, gives you the density, how many people from this 5-mile beach live within 2 miles of the water shore? Obviously not drawn, just guess. Okay? Now, this is the key to getting started on many of these. Use units to guide you. Our question is how many people? What kind of stuff are we given? What's the density function unit? People per
Square mile.
square mile. So the density function is people per square mile. Now, we want people, so to get number of people, we'd have to take the density and multiply by
Mile square.
miles squared, and that would give me people surely. Now, the thing is this, that density function varies. This is not a constant times an amount of square miles. This is a varying factor times an amount of square miles, and so you're going to need to make lots of little calculations. For example, you could say, all right, in this one little sliver, how many people? How would you find out how many people in that one little sliver? D of x times the area of that little sliver. Area of one sliver. So talk to me about that little sliver. Dx wide and maybe you're overthinking. It's just 5. Okay?
I didn't know that.
5 dx. Okay? What is, now the limits of integration, x is the variable of integration. And what does x represent? Distance from the beach. So what kind of region of x do we want to integrate over? Within 2 miles of the beach. 0 to 2. Throw that into your calculator. I think you'll agree that the units do work out as people per square miles. 5 is in miles. Dx is in miles. That does give you people. Count it to the nearest whole person.
It is charged.
And get 100. I got 139. Did I type it in wrong?
I got something
Oh, I
way
forgot to
too
multiply
much.
by 5.
You didn't get 139.
I got 139,755. That is exactly.
139,756 people?
Yeah.
Okay. All right, you get the gist. Okay, you try one. Yeah, it's a little more complicated if it's not, so we'll go with perfectly circular. It's when eight fingers.
So do we do the x and then do we multiply by the
Why is it area?
That would be funny. No, it's just one x.
Oh.
Yeah. Okay, are we ready? Shut up, your answer. Go on it. Go ahead. 46,000, 498.
Whoa, I'm not done yet. That's what I got.
Negative? Negative's not good. 498?
I got a negative.
Yes.
Got a negative 1,000. 7,367.
Okay, let me, you are obviously in the right ballpark, most of you, not negative, like, but, you're on the right track. I assume you integrated with a dx in there, and over here you looked at some kind of area calculation, yeah?
Yeah.
Okay, so, what did you say for the area? Did you say pi r squared, or did you say pi r squared minus r squared, or what did you do?
I put dx.
Okay, x and r are the same, so it could be pi x, that's fine. X is the radius, so you're cool. Pi x squared. Did you do that, or did you even get started?
No.
Where'd you get your answer, I guess, is my. Just integral, you just integrated d? Wait, okay, wait, the units on d are people per square mile, and then you multiplied it by dx, which is miles?
Oh.
You just found people miles, that's not. So, no, dx squared is definitely, that's a very thing, if you ever have squared dx, you're in the wrong class. Okay, so, that's a no. You need to find how much area is in this ring.
Yeah, wouldn't it be just
Pi r squared, isn't that the area totally within?
Yes, so it's
Okay, what? Okay, now you're starting to get somewhere. Now, keep in mind that I know you, throughout all algebra, you definitely did this way, yeah? But keep in mind that it's not even that wide. It's this wide. And not actually even that 10 is too thick. It's not even that wide. So if I asked you to find the area of this line, how'd you do it? Bigger minus smaller. Okay. What if this was a string, and I said find the area of the string? Would you keep it round? No, you would straighten that out. So you would, okay, now how long, what's the base of this rectangle? 2 pi r, or 2 pi x, yeah? What's the thickness of that rectangle? Yes. So it is dx times 2 pi x dx. Last hurdle. What's the x range?
1 to 3.
1 to 3. You got that. That's good. 3. 1 to 3 is, this is a pi. 1 to 3, x represents.
1 mile of lake and then 2 miles.
Yeah, x is the center of the distance from the center of the lake. So you have to get from 1 just to get people. So I got something like 4,579. Okay, that's a good one. All right, that'll come later. Would you get your homework from yesterday? Yes. What? That's the nature of it has to be super. Okay, here we go. I am going to give you a quick run through of my answers, and we'll go back and go over questions in a minute, but first I need to. So this will not be enough work for you lazy readers to just write down and say, ha, I did it. No. It'll just be verification for the people that did do it. Yes, you had the right idea, or no, you need to go back and figure out what you did wrong. So for 1A, we did the whole top half as an example, so you should be done there, yeah? 1A, did you get 7.6 meters per second?
Yes, I did.
Okay. And you were careful with your approximation signs, right? Okay. This guy, what did you say this integral gives? The example was displacement, but this problem is not V, it's distance. Now, just to make sure you're totally with me, all right? So I'm going to take a little walk here. If I go, I think I've talked about this, we'll talk about it again. If I go this way, 1, 2, 3, and then I go back, 1, 2, 3. What's my displacement?
0.
What's my distance?
6.
Now that distance came from taking the direction component out of it. Instead of saying this way 3 and that way 3, it's just you went 3 and then you went 3 more. I don't care which direction. Well, what math process removes sign or direction?
Absolute value.
Absolute value. So this integrating speed gives you distance. That's what speed, right? Do you agree that absolute value is speed? So this, now remember when you interpret, they look for 4 things. So talk to me. This integral is the
Distance.
This is the distance with
In
units
meters.
in meters. Now when it is from
T equals 0 seconds. T equals 5.
0 seconds
15
to
seconds.
What I said.
equals 15 seconds. Okay? My answer was, okay, now
372.
I got 66 is wrong, it is 78. Now if you got 66, it's because you integrated and you took velocities, not speeds. It is 7 minus 0 times the absolute value of V of 0 plus 9 minus 7 times the absolute value of 7 plus 15 minus 9 times the absolute value of 9. So again, 66, you use the signs, the negatives, and that's why you came up with 66. It should be 78 meters. Okay?
Can you explain this next one?
Sure.
That made no sense.
Okay? So obviously at time equals 0, velocity is 0. So velocity is 0. Actually, let's go back. Do you agree not moving means velocity is 0? Okay, cool. Obviously from the table he's not moving at time 0. Is there another time when he is not moving or velocity is 0?
Yes.
When?
Between 7 and 9.
Between 7 and 9. Why?
Because
Because
it goes
it
negative
changes
to
signs
positive.
and has to go to
If velocity changes negative to positive, it must pass through 0, assuming velocity is continuous. Can we assume velocity is continuous?
yes.
You can. Okay, so it would go something like this. Velocity is continuous, and now I write this in symbols, but in my mind I say this totally different. And velocity equals 0 is between velocity at 7, which is negative 3, and velocity at 9, which is positive 12.
No, so we don't have to like actually find the time.
You cannot. There's no equation. It cannot be done.
That's what I was confused.
So by IVT, there is a time in what interval? 7 to 9 when V equals 0 and therefore at rest. You follow?
Yeah.
Okay. This, given you have velocity and you have an initial position, how do you find position later? So I could actually integrate the antiderivative, find the position, find the C. You could do that, or you could do a definite integral. What did you do?
12 plus the integral of velocity
Oops.
from 0 to 10.
So x at 10 is x at 0 plus the change in position, right? Are we just doing the original position plus the displacement or change in position over the time frame? And I got negative 58.167.
I did
16 what?
67 flat. Instead of negative, I changed
left of the origin. Okay. Don't do that on the AP test, so that's pretty easy. Okay, just leave the negative. All right. This, how do you put this on a BC exam? This is a free response question that comes every couple of years. This one's a little harder to interpret. People know how to interpret this. They know this is displacement, and they know this is distance. That's very rarely missed. But when you integrate acceleration, I can't get my mind around that. I'm doing lots of little meters per second squared times second calculations. Well, unit-wise, what is meters per second squared times seconds? Meters per second. So it seems like this has something to do with velocity, huh?
Yeah.
Well, that's where it helps to think fundamental theorem. When we do the fundamental theorem, we take the antiderivative of A, which is V at the upper minus the lower. Now, given that these two things are equal, maybe you'll have an easier time interpreting. The integral gives you the change in velocity. That's exactly right. It's the change in velocity. Now say what it is with units and when it is with units. Change in velocity in meters per second. Time equals 0 seconds to time equal 8 seconds. My estimate was 100 meters per second. This one is defective, but I'm going to keep it because when I wrote it, you probably, well, let's just get into it here, okay? When is the person moving the slowest? Now, do I look at these numbers, 0, 11, 8, 14, so boom, slowest to 0?
Probably not.
Okay, no, because movement means how fast you're going, and that's not acceleration. Do you agree? So when is it moving the slowest? This is the change in the velocity, and we just said that approximately, the velocity is increasing approximately 100 meters per second. So, when is it moving the fastest, the slowest?
From 2 to 4.
If velocity is increasing constantly, then when is it moving the slowest? 0 makes sense. That's not necessarily true. Why not? So let me give you case one. Case one, his velocity at time 0 is 0. And then over time, he gets faster and faster. In that case, when is he moving the slowest?
0.
0, okay? Case two, his velocity at time 0 is negative 100 meters per second. Now, what is his velocity at time 0, and what is his velocity at time 15? Starts at negative 100, so he's moving fast then in a negative direction. And at time 0, it's 0. So the problem then is it would depend on if velocity is positive or negative. We don't know. If he was always moving positively, then he would, and his velocity was constantly increasing, then he would be slowest at the start and fastest at the end. But if he was moving negatively, then he was probably fastest at the start and slowest at the end. All right. This guy, estimate the amount of trash brought in during the 7 months using a right Riemann sum. Did you get roughly 9.7 tons? Okay. If the trash decomposes at a rate, is the amount of trash increasing or decreasing at time 3 months? This was hard for the last class. What do you say, increasing or decreasing?
Increasing.
Increasing, why?
Well, you have to do the definite interval. Or wait, no.
You do not need an integral to do this problem.
I'll choose plug in 3.
Into what?
The function of dt.
Okay, so if you plug 3 into d, you get d of 3 is 0.739 tons per month.
Yeah.
Okay, great. Does that mean, do I then say, well, that's positive, so it's increasing?
No.
No. What else goes into how fast the trash? Yeah, you also have to consider I of 3. I of 3, according to the table, is 3 tons per month. Now, does the decomposing subtract trash or add trash? this subtracts trash. And does the in rate add trash or subtract? Adds trash, all right? So one is removing trash, one is adding trash. So they're a fighting rate kind of problem. Which one wins?
Increasing trash.
The increasing, the in rate is greater, so it must be the case that the amount of trash is increasing. You'd say trash is increasing. How would you justify that?
I of T is bigger.
Because I of not T, I of 3 is greater than D of 3.
Is it okay if I said I of T is bigger than D of T when T equals 2?
Yes, absolutely. Okay. Given there are 15 tons of trash at times 0, how many tons of trash at times 7? I have 14.897 tons. Do you agree? Okay, there are 3 components to how much trash. What are the 3 components to the amount of trash?
Initial.
The initial, so time, what's the question? Times 7. Tons at times 7, T stands for trash tons. Okay, so you say tons at 0 plus
Increase from 0.
how much it, I'm just gonna go just generically speaking, how much it increases minus how much it decreases. So you already have one of these. Didn't we already find in part A an estimate of how much it's gonna increase by?
Yeah.
Okay, so from part A, we say it's gonna increase by 9.7 tons. How do you find out how much it's gonna decompose or decrease by?
100.
The integral from 0 to 7 of E of T dt. Okay, that's where I'm getting my. Pretty cool? Okay, 3, this one, where did you start?
P equals X, Y.
P equals xy, okay, and then what?
Which equals
Something for Y.
1.
Okay, something for y, the function for y, cool. Did you clean that up before taking your derivative?
Did not.
Oh my word, that's
1 minus X over square root of X.
I didn't know that was mathematically correct.
distributive property?
Like,
Yeah, that's a thing.
Colin.
Should it be minus?
People don't even have it.
yeah.
Yeah,
Okay.
it should be subtraction instead of addition.
Oh, yes, sorry, it is subtraction, thank you. Okay, all right, so there's your product equation, cool, that's actually the easiest part. Then what?
Then I took the derivative.
Took the derivative, and you'll get a fraction, you get a common denominator, and you'll have to find the critical numbers. The critical number is x equals
0 and 1/3.
0 and 1/3, and thankfully they didn't put 1/3 as a distractor. That should have been there as a distractor. They wanted the product. So after that, the stinker is you had to say, all right, when x is 1/3, what's the product? It's a stinking mess. This book uses tons of algebra. You had to do all this rationalizing. It was a mess. But the answer was C. And I expect when I grade this, I will see your algebra behind it. For 4, I have B. Oui, oui.
Good morning, Dublin Jaguar. Please rise to the Pledge of Allegiance. Please begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. All students, it's back! The Career Exploration Series begins the week after Thanksgiving on Tuesday, December 3rd during 7th hour Eastbound schooling. The first topic will be law, a path to prosecution. Have you ever wondered how it really is in a courtroom? Mark your calendar now and check it out. All students are welcome. Students, lost and found is in the front lobby by DJ the Jaguar. Please stop by to check for any lost items. We will donate the items on Friday, November 22nd. Colorado Academy is hosting an athletic recruitment presentation today at 6:30 p.m. on their campus. Guest speakers from Lawrenceville School in New Jersey are experts on the topic of athletics and present at colleges and high schools nationwide. They have invited Devlin to join them for this informative evening. Stop by counseling for the details. Hey guys, this week is the Spanish Brothers Society Dance Food Drive. Please remember to bring cans to your third period class to provide for those in need.
Somebody brought cans, good job. I'm gonna do some tonight, Donnie, you should too.
Second is Carson with 207, and first is McAllis with 314 cans.
Oh,
You
wow.
got 4. Come on, people.
They didn't even mention us.
Tickets for all of the
That's
games
wonderful.
are on sale during lunch. The cost is $5 per ticket. The performance is Thursday evening, November 21st at 6:30 p.m. at the West Bowles Community Theater. Any students who are going to Disneyland with band, choir, or orchestra should sign up.
A must be what, negative or positive?
Sign up sheet is posted between Miss Patch
If it's a max,
If you're looking for a relaxing but festive 7th hour this Friday, your Sources of Strength has got just the thing. Come down to the auditorium during 7th to watch a Charlie Brown Thanksgiving and get into a thankful spirit before break. Make sure to sign up in counseling on
but
Friday.
you cannot. I didn't give enough information to find it. Yes.
Sign up early because it will fill up. See you Friday, Jack.
What?
Was the answer D for
Senior high students, members of student advisory, there will be a meeting this Thursday, November 21st during 7th hour in room E100. Please inform Mr. McWhorter if you are unable to attend. Attention peaceful school participants. We will be meeting in Mrs. McSimmons' room today during 7th hour and then going to Pfizer for our final visit of the semester. See you then. Hey Jack, it's time for your daily day of the day. Happy Peanut Butter Fudge Day. Jack, this whole week the DHS cheer team is selling DHS distributed Pura Vida bracelets. All proceeds go towards making an awesome Sadie Hawkins Day, so bring your money. They make great Christmas gifts too. Get yours now before they're gone. Boys basketball is looking for 2 or 3 managers for our lower level team. If you are a 9 to 10th grader, that
8 is A, 8A is 8,
Thank you.
AP is 2.
Mr. Rickman?
Yep.
For A, I got 16.
That's all your announcements, guys. Have a great day.
Isn't it from 0 to 4 5, not 2 5? Wait, what do you get? I got 16. I'll do it again.
Don't tell me you want.
Oh, it's 2 sign-ups. Oh, you're right. It is 16. I didn't get it signed. Sorry, this should have been Tommy.
That's what's up.
Not a boy. It is 16. You're right. This is 2. This guy is 36. And this is 3 log 2. All right. If you need to keep this and turn it in tomorrow, either because you're a total wiener who didn't do your homework, or because you just missed a lot, gave it your best go, you missed a lot, then you may turn it in tomorrow. So rather you turn it tomorrow with good than turn it in today with garbage. Okay? Your homework is still 62 though, so either way, do 62 tonight. And seniors, I'll try and go lighter in your homework tomorrow, so you guys do your fishing, particularly Thursday.
We had to have I didn't have any time to